This video will go through solving one of the examples and creating an exponential smoothing forecast. This is the example described in the lecture for Lesson 7, as well as the solved example shown on the Example 2 tab in the dataset. What's provided is 12 periods of actual demand for a product, and the quarter, these are quarterly demands, so those are listed, and then the demand is actually listed in the actual demand column. Exponential smoothing is an averaging method that comes up with the current forecast by using the previous forecast and adjusting the previous forecast for a percentage of the forecast error. The forecast will be calculated in column D. The ES stands for exponential smoothing. With exponential smoothing, we need a starting assumption for the forecast. One common starting assumption would be to just make the first period forecast equal to the actual for that same period. The exponential smoothing forecast is defined by the smoothing constant, which is sometimes denoted by the small Greek letter alpha. This example will just start with a smoothing constant of 0.5. Alpha will be a number between 0 and 1. Since the first period actual equals the first period forecast, we start by calculating the forecast in the second period. The formula is equal to the previous forecast plus the smoothing constant times the previous forecast error. A forecast error is always calculated as an actual value minus a forecast value. This number is in parentheses in the formula. The dollar signs entered in the formula on the row and column for alpha, the smoothing constant, will ensure that when we copy this formula down, alpha is always referenced from cell D2. Once we've created this formula for the exponential smoothing forecast, it can simply be copied down. I'm first going to just copy it down through period 13. The goal here really, of course, is to forecast future demand values for this product. Period 13 is the first future value. If I were to copy this beyond period 13, you notice a problem, and the problem is because the forecast for period 14 depends on an actual for period 13, and there isn't an actual that exists for period 13. So if we want to carry forward the exponential smoothing forecast beyond period 13, one way to do that is in the actual column, just reference the forecast. So if we want to continue rolling the forecast forward, we'll just have to use the future forecast values to do so. So I'll do that in column C and copy that down, and do this in column D, copy that down. Now, exponential smoothing is an averaging method, so of course what happens when we roll that forward beyond the next period is we simply see the forecast flatten out. It's an average. The thing about the exponential smoothing forecast is that it's actually a weighted moving average of all the previous actual values. I'll also calculate the mean absolute percent error here on the sheet. This gives us a measurement that shows us how effective this forecasting method is. The forecast error will be the actual demand minus the exponential smoothing forecast. When I calculate an error measurement for an exponential smoothing forecast, I typically prefer to start with the second period because I know that the first period forecast is simply an arbitrary forecast, basically as a starting point to start the series. The true error measurement would come with the second period. The forecast error then can only be calculated for the periods where there's a true actual demand value. So this error formula is only copied down through period 12. The percent error is going to be calculated by taking the absolute value of the forecast error and dividing it by the actual. We take the absolute value because, of course, the error can be either negative or positive. We might miss the forecast on the high side or the low side. The absolute value of the error is divided by the actual to state this value as a percentage. So it helps give us some perspective on how large the errors are. Again, this forecast is only copied down to the periods where we have actual demand values. Up at the top, I'll go ahead and calculate the mean absolute percent error. And it will simply be the average of these absolute percent errors. We can interpret this as a percentage. With a smoothing constant of 0.5, the exponential smoothing, in this case, produces errors that are about 8.6% of the actuals. We could use this to compare the exponential smoothing forecast to other competing methods to try to select the best forecast. One thing we can also do is use this error measurement to try to improve the smoothing constant for the forecast. We do this by using Solver. Solver is shown on the data ribbon at the far right. It's possible that you'll need to add Solver in. To do that, you would go to File, go to Options, click on Add-ins, and then at the bottom of the screen we have Manage Excel Add-ins, and if you click Go, you can see that the Analysis Tool Pack is added in on my machine, as is the Solver add-in. Most of you are familiar with add-ins from using the Excel regression tool. Once we have this added in, I'll bring up the Solver window. The objective here is going to be the mean absolute percent error. I have that calculated in F2. We want to minimize that objective, so we'll make sure that the Minimize button is selected. We want to minimize it by choosing the best smoothing constant, and I have that in cell D2. The only constraint that we need is that we want the smoothing constant to be less than or equal to 1. I'll delete the one I have in here and just demonstrate adding the constraint. I would click on Add, click on my smoothing constant. I could change the inequality in the middle, but less than or equal to is what I want. And we'll put 1 in the right-hand side of the constraint. I actually also want the smoothing constant to be greater than or equal to 0. That's handled by checking the box here to make unconstrained variables non-negative. The solving method for this problem will have to be GRG nonlinear because the mean absolute percent error is a nonlinear objective function. I click Solve and click OK and find that the best smoothing constant for this data is about 0.46. So this will show you at least a little bit about using one of the forecasting methods and calculating one of the forecasting error measurements, as well as using Solver to find the best parameters. Of course, we're covering other forecasting methods, and the lecture should give you some information to try to replicate those calculations, as does the data set posted with the lecture for this week.